Welcome back to part 4 in the DIY digital watch series. Yes, we finally have something that I can wear and I can't wait to show you how we've got to this stage. It's been a while since part 3, so in this video I'm going to cover everything from where we left off to where we've got to now, because a lot's changed. So first, let's recap how we got to this stage. So the project was born after I bought a digital watch kit from the internet and was pretty disappointed with what I received. So I thought I could do something a little bit better. And this started my journey into designing and developing a new Arduino based digital watch. And I've decided to document the whole process from concept through to build on this YouTube channel, so you can see exactly how I come up with my ideas and how I develop them. And in the last video, I managed to get a fully working movement on the bench. Now, yeah, there are a few jump wires, but it did work. And there's only a couple of little improvements I want to make. I'm going to take you now from where we left off in the last video. And I'll cast your mind back. The last video ended with a PCB working on the bench. It would show the time and display, and I could program it from my computer. So let's jump in to where I've got up to. So whenever I'm starting a new 3D printed watch design, I like to start from the movement and work outwards. This way you're not going to cause yourself any issues further down the line with when you're actually designing the watch case. So here you can see me coming up with a bit of a bracket in SolidWorks that I want the PCB to fit into, and then I can use this core to work outwards and start to develop the rest of the watch case. This also gives us an indication of limitations as to size. So once this was working, I got that printed up and it all fit fine. That wasn't really going to be a problem. The next part was to work out how I was going to interface the switches with the case. And as you can see here, I've kind of expanded that case that you'd just seen first and added a little slot for a switch. These are some really easily accessible tactile switches which work great for this scenario. So you can see there, I've managed to get to fit to the case really nice and snug. I've got my two contacts which I can then wire into the PCB. So this here is another little bracket. Now what this is going to do is hold the glass in place and hold the PCB in place. So once you tighten it all together, everything will push into one another and have a nice fit. So there we can see that's the PCB and the switch working. Now there's a bit of play there. You can see a bit of play in that case. So I head back to SolidWorks, I reshape the switch segment of the case. There's a couple of other little changes I needed to make at the time, but I'm always measuring using my calipers and the model. I just find it easier to work this way. Everyone has their own ways of working, I guess. So my case is now developed. I put some lugs on just to have a look for size. I've had to go for a 24mm strap, which is big, but it's kind of smartwatchy size. I think the Samsung smartwatches are about this size, so it shouldn't look too out of place. So I hit print and got this first case to print, and this is where I start getting really excited. This is starting to look like a watch now. So we'll pull this out of the printer. There's a bit of string in there, that just needs cleaning up. And look, I got the movement from the last video installed into the case just to check for fitment. Now obviously in that you could see that the wires were still coming out the front. So what I decided to do next was to solder up a new PCB with a new chip so we didn't have those wires on the front. I bought this little ZIF, which is zero insertion force socket, so I can program the 80 mega chips separately from the board. I was experimenting here with a hot air solder station, which is new to me. I've never used one before, and I just had loads of problems. I really messed up this board. After a lot of trial and error and just using a lot of wick to unsolder various parts, I kind of gave up with this. I had to reorder a few parts. Whilst I waited for the rest of the parts to arrive, I decided to take the PCB that I'd built originally, unsolder some of the jumper wires and throw that into the case. So I managed to put the case together and start wearing this thing. On a bit of a whim, I decided to upload this to the Arduino subreddit, and it kind of took off a little bit. There's a lot of excitement behind this project, and I've got a lot of questions that I want to address. That's kind of why I'm pushing this video forward a little bit. Probably the most asked question is power consumption. How long does the battery last? How am I managing that? What battery am I using? So to finish this video, I'm going to sort of deep dive into how I've worked out my 6 months battery life claim, and I'm going to show you what I'm doing to save power. I've also been asked quite a lot about how this thing works. Now, I have gone over this already in, I believe, part 2. I run through how the project works on a breadboard. So do go back to video 2 if you haven't seen that already. So I've set up my new PCB that I've soldered up recently. Here's the original watch that I'd posted to Reddit, but we're not going to be looking at this one. I'm going to be looking at this new PCB that I've wired up. So this is it. It's a lot neater. It looks a lot nicer. I'm going to run you through how I've come up with the power consumption assumptions. So at the moment it's in sleep mode, and we can see it is running at 15 microamps, which is tiny. So the device is currently in sleep mode. The switch is an interrupt. So when I click that, we then go up to 11 milliamps. So in 11 milliamps, the device is running, it's displaying the time. And then as soon as that display goes off after the 10 seconds, it drops back down to 14 microamps. And that's it really. I've got the battery set up here. I haven't got it plugged in, it's just so I can run the ammeter. So I'm going to show you now how I calculate how this translates to 6 months battery life. I've created this quite simple Excel sheet. I'll make it accessible so you can play around with the numbers yourself, check my workings, and see if you spot any mistakes. You could also use this to sort of play around with how many clicks you can get away with a day, and if you wanted to increase or decrease the display time. So if we look up at the top corner, I've got the battery capacity. Now for a CR2032, this is a typical capacity. What we could do is though, we could lower that to 200 just to allow for any environmental changes or the battery curve of the battery itself. We're not going to get the 3 volts for the entire lifespan of the battery. So we'll put 200 just to allow a margin of error. We've then got the display time, which is being programmed at 10 seconds. You can change this on the code very easily. It's a variable, so you can just change this from 10 to 20 or down to 5. And then I've converted this into the equivalent in hours. So that's 10 seconds equals 0.0028 of an hour. We've then got our sleep current and wake current. This is what we've just measured. Got 15 microamps and 11 milliamps. Clicks per day, I've put 12. This is kind of, I guess, 1 click an hour, or we could put that up to 15. We could change that about. We'll leave it as 10 for now. And all I've done here is taken the total number of seconds in a day and subtract the wake time off it. So whenever it's not awake, it's obviously asleep. And then converted them up into hours. So you can see here it's a very small fraction of the day that the device is actually going to be awake. It's, very small. Now if we take these values, we can plug them into the runtime. I've taken the battery capacity and divided it by the 2 currents. So the first one is, this is the sleep current. So this is the amount of hours that the device would run for in sleep. And that is a long time. For example, so if we do that divided by 24, 555 days, it'll say in sleep. 18 hours is how long it'd run if the display was on full time. So we can't do that because a watch is pointless if it doesn't even run for 24 hours. What I've then done is averaged it through, so basically multiplied both these values by the percentages, and added them together. So that gives us an average power consumption per day. 554.9 days, which turns into 1 year and 190 days. So let me change that a little bit there. Boom. So 1 year and 190 days, which is a lot better than I originally calculated actually. when I'd done my first calculations, it was on the breadboard. I had a different MCU. I was using the dip version, not the surface mount version. So maybe that's lowered the power consumption. And what we can do here is we can just play about with the numbers. So if, let's say you wanted to display the time for 30 seconds rather than 10, we'll change that. You can see it lowers the time quite a bit. And let's say we're going to click it 30 times a day. See, even there, we've still got bags of power. Over a year is a great amount of time for this. It's not quite the 10 years you get the Casio, but we're using LEDs here. I guess what this means is we're not going to be limited to what functions we can put on the watch. My sort of big picture for this would be to have other buttons and other functions on the watch. Some people have mentioned maybe a thermometer or different sensors, I don't know, accelerometer, so it detects when you rotate your wrist. That could be quite cool. But to start with, it's great knowing that this watch is going to last well over a year just in the watch mode. It's a bit better than the 6 months I'd originally quoted. So yeah, we're well over a year now. Let's put these back down to the times we were looking at. Display time, 10, clicks per day, 10. And there we go. 1 year and 190 days. Now if the battery performed its best, we've almost got 2 years. So there might be some minor improvements we can make to these to try and get to 2 years mark. That'd be a great achievement. But that's what we've got for now. So this brings me nicely onto the next steps of the project. Now, a lot of people have been asking when can they get hold of this, how they can get hold of this, and how they can build it. Now, my plan is to put this PCB into production so I can sell a fully assembled, fully programmed PCB. This means all you'll need to do is 3D print the case and put it straight in. I've got a few issues I need to sort out before I do that, but I'm on it and I'm wanting to release this as soon as I can. I'm waiting on a few quotes to see how much it's going to be to put in production. Once I know that, I can start putting a price out there and maybe even taking some pre-orders. If you want to be the first to hear about it, I've set up a mailing list on my website. There's a link in the description. If you enter your email on there and your name, I'll let you know first when this is going to be released. I've also put a couple of questions on there, such as, do you 3D print? Can you program Arduino? And I'm asking you, what is a fair price for this? How much are you prepared to pay for a fully assembled, fully programmed PCB? And unfortunately, that is all we've got time for today. If you've enjoyed this video and you're enjoying this project, please hit subscribe. It really helps me out and I love seeing when I get new subscribers. We're almost at 500, so let's see if we can crack it this weekend. It would really make my day if we could. I've got more content coming for 3D printed watches, Arduino, electronics, and the rest. I've got loads of video ideas coming up, so do subscribe so you don't miss out on any future videos. But as I said, that's all we've got time for today, so let's roll some B-roll of the new watch and let me know your thoughts, and I'll see you in the next one.